Okay, we proceed with example 2. In this example, we make the addition of both of these number, and again, this is gonna be straightforward. It's clear it's addition operation. And the same thing we did with example 1 by this is the initial step by converting these values into their binary representation in the format of IEEE 754, and this is exactly going to be stored in memory. So we do this for the first number, and the second number, the same thing for the second number. Now we move to step 1, which is a straightforward step by extracting the mantissa or the first and its exponent, and then we put the leading one by adding point and then 1. Very straightforward. The same thing we do for the second number. Now in step 2, we have to subtract the exponent to find the difference, so we're gonna use it for shifting right the smaller exponent mantissa. And when we subtract, of course, the exponent. When we make the subtraction, the result in here is 10, which is in decimal 2. So we have to shift now which one is smaller. Okay, we see this exponent is the smaller one. That means we will right shift its mantissa 2 places to the right. And at the same time, we increase this one by 2. So in that case, it's going to be equal this exponent. And that's the final result or target of this step. Okay, now in step 3, we will make the shifting. It's straightforward, as we saw in last example, example 1. This is the leading, this is the point. We added 2 places, 1, and then we put 0, and then we put another leading 0, as in this case. So this one is this one. This is 0, and then point 0. And then we move now. In this case, as you can see, after you make the shifting, you have to increment the value of its exponent by 2. So that's why it become 1501110. Sorry. Okay, now let's not forget about the leftover, which will determine our GRS. We talked about the guard, or these bits that use for roundation. Now, since they are 2, which is in this case 1, we have, for the sticky bit, it's going to be what? 0. And this one has no leftover. That's why we put 3 zeros. Okay. Now, we move to step 4. In this step, we perform the addition. Now, when we add these, it's going to be 110, of course. And when we add this one, 0 plus 1 going to be 1, 0 plus 1, 1. 1 plus 1 going to be 0, carry 1, 1 plus 1 plus 1 going to be 1, carry 1, etc. And we come here. And in this step 5, after we get the result, as you see, now also we do not need a normalization, because the point here is next to the 1, so it's already normalized. So since it's already normalized, that means we have no normalization needed. And we go to the step 6, which is rounding. In rounding, we already remember the rules, for rounding. And in this case, rounding meaning adding 1 to the mantissa. And in this case, when we see that the GRS equal 110, that means we have rounding. We round by adding 1 to the mantissa. So the final result gonna be like this. Of course, there is no renormalization, because when we added the 1 here, it did not make carry in this place, so no need for renormalization. Okay, now this is the final result. In all final step, we wrap up the result by putting the updated mantissa and the exponent, and finally the result, the sign bit, which is we get it from both signs, because this is going to be 0 because both signs are zeros, and this is addition operation. This is for example 2, and I hope the steps are clear. We did the same thing by converting the result into hexadecimal. As you can see, if you do that in hardware, if you add these 2 floating point number, this is the result gonna be. This is in hexadecimal format, and this is in binary format, which has the IEEE 754 format. I hope this example is clear, and so let's go and move to example 3. Okay, we move forward with example 3, and in this example, we make this operation, which is says minus 511.571 minus 16.4168. As we saw before in second slide, that is this going to be addition operation or subtraction operation? We saw by the compiler will make it addition operation. By adding the negative value of this number, he can add it with this negative value of this number. So we do not have subtraction here. If we make subtraction, is different to process. It's much more complicated subtraction for the floating point number, which we're gonna see in later videos. Okay. Now, so let's proceed with this one. As you see here, we have to convert this one to its binary representation using the IEEE 754 format. Notice here now we convert the minus value, the negative 511.571. So that's why you see its sign is going to be what? 1. This is important. We do the same thing for the second value, which is going to be negative, and now we make addition of them. Okay. Now we go to step 1, which is the same steps we saw in earlier examples, and we make we subtract, we extract the exponent and the mantissa for each digit, and then we put the leading one by using 0.1, the same thing for the second digit, and now we make the subtraction as normal of the exponent to determine the difference, so we can get the shifting amount needed. In this case, again, it's 4. This 4 is the shift amount, is the right shift amount needed for this mantissa because its exponent is the smaller one. So we're gonna right shift this mantissa 4 places to the right, and we increment the value of this exponent to be equal to this one. Okay, now the shifting is straightforward. We already saw that. We make this one, we move 4 places, and then we put it the leading 0, as in this case. So we move the point, it was here, then we moved 1, 0, 0, 0.0, and moved 1, 2, 3, 4 places. That's why this is the result of this subtraction. This is the shift amount. Okay, now when we right shift amount 4 places, we incremented the value of its exponent. Now both are equal, and this is the whole target of this process. Now, let's not forget about the leftover. In this case, the leftover is 1011 of this shifting, and the leftover of this one gonna be 3 zeros. This is the GRS of this one, and the GRS of this one gonna be 101. We just care about only the most significant 3 bits. Okay, now we make the addition. The addition is straightforward. This is gonna be our GRS, of course. That when we make the addition, 1 plus 1, 0, 1 plus 0, 0, 1 plus 0, 1 plus 1, gonna 0, carry 1, 1 plus 1, 0, carry 1, 1 plus 1, 0, carry 1, 1, etc. We get here. And here, after we finish the addition, completed the addition, now we go to normalization. And normalization, we need normalization here. Because as you can see now, if you look to its right, we have 1s, and the closest one is this one. So we have to move how many steps? We have to move only 1 step, as you can see. So in this case, yes, we need the normalization, and we normalize it by shifting right 1 bit, and we have to increment the exponent. Now this is important. In this case, we move this point to the right 1 place, and then we add 1 to its exponent. But notice here, when we right shift, we have to push this whole number, so we have 0 left over, and this 0 left over, it's gonna be put with the GRS we already have, as you can see, and this point is very important. So in fact, we're dealing with the GRS as part of the mantissa. So in this case, when we make the right shifting 1 bit, first we added 1 to its exponent, and the second thing, we put the leftover bit in this case, and pinned it next to the GRS. So now the new GRS is become 010 in this case. Okay, And as you can see, now this new GRS, after we make the 1, when we added 1 to its exponent, now this is the updated exponent, and the updated GRS is 0, 1, 0. Now in this rounding, is there rounding in here? As you can see, no. There is no rounding because GRS equals 0, 1, 0. If the GRS, if we did not put the 0 in here, the GRS will be 1, 0, 1, and it has to be rounding. But this is the correct answer, is that let's not forget that when we pushed the leftover bit, which is 0 in this case, it has to be part of the GRS. It's the G bit actually. So in this case, there is no rounding. Now, the no rounding happened because we put the 0 here. Where did we get this 0? We get this 0 from the leftover after we make the right shifting, as you can see in normalization process. If we did not put this leftover 0 in here, and the GRS will remain 1, 0, 1, and in this case we have to make rounding by adding 1. But this is going to be wrong answer. So the correct answer, as in this case, there is no rounding, and of course there is no renormalization, and this is the final result. Now in here we wrap the final result by putting the updated mantissa. As you can see, of course there is no rounding happen here, and then the updated exponent after we added the 1 here because we made normalization. And the final thing is the sign bit. Why we put the sign bit is 1? Because they both are 1s. They both are negative number, and we make addition. So now it's clear. The final answer in this case it's in hexadecimal format, in decimal format, and this is in binary format, which follows the IEEE 754 format. And this example, we reach the final example of the addition operation. Next videos we will talk about the subtraction into more detail. I hope everything is clear, and I see you next time. Thank you very much.